Welcome you all to this course on defects in materials. Okay. In the last class, we have covered basic elementary part of the tensor which is required. Okay. Essentially, tensor is nothing but an operator which describes the property of the material. Okay. So, the property of the material we are wanted to find out. Essentially, we should have an input signal and an output signal has to come out. That is how a property is being defined. So, the input could be like, for example, if you apply a voltage, we can measure the current density which is there in that direction. Okay. That gives information about the conductivity of the material or the resistivity of the material. Okay. Similarly, various instances, magnetic permeability, you can think of lot of instances even in electronics or even X-ray scattering if you wanted to look at it. We have an input signal, we have an output signal which comes. What these two relate? These two relate the property of the material. Okay. That property of the material can be, if we take with respect to a coordinate system and try to represent it, because that is the way, otherwise everyone will be using different type of a coordinate system. So, if we define with the vectors with respect to a coordinate system, when we look with respect to that coordinate system, then we will have 9 components of the independent 9 components are required to represent the property completely, correct? Or with 9 components the property is represented. Okay. In the case of materials, when we talk about deformation of material, in this case also we use 2 properties. One is that stress and strain, these are all the terms which we use. That is, if we deform a material, okay, and try to pull it, we say that there is a stress which is generated in the material. Okay. Both the quantities we call them as tensors. Okay. What is the reason for that why we call them as tensors? But generally the way we think about that is they are like any other quantity, like a vector, but that is not the case. The reason essentially is that, let us take the case of a strain itself. Okay. In the case of a strain, the strain relates displacement and position of an object. Okay. So, position is also a vector, displacement is also a vector. Okay. I pull this sample along, okay, and the sample dimension increases to, it says, this side is being held rigidly. Okay. When this gets some extension, okay, let us take it to be some value, that is from L0 initial length, it becomes a length L. Okay. L0 minus L minus L0 by L, we call it as the strain, correct, or elongation. This is the terminology, elongation is the terminology which we use it. Okay. In this, if you take half the length of the sample, okay, what is going to be the displacement? It will be some displacement will come, that is essentially given by the displacement is strain into L0 by 2, correct. That will be the extension which we are seeing it here. No, here it is L0, sorry, this is L0. This what it gives is essentially the displacement, correct. The displacement equals some quantity which we measure. So, it is what it relates. So, in terms of vector, if you try to represent it, position is also a vector, okay, in terms of coordinate system if you use it, displacement is also a vector. So, 2 vector quantities are getting related. So, it is a second rank tensor. Okay, apart from that, what we know of it is this, we call it as an elongation. Okay. This is one way in which a sample can be deformed, or we can bring about a change in shape to the material. What is the other way in which we can bring a change in shape to a material? That is essentially what we do it is that Suppose we take a sample like this and apply some stress, then the sample shape change in shape, correct? So this angle theta, okay, the tan theta will be equal to, if the displacement in this direction is x and this height is L, and this we call it as the gamma, the shear strain. This is the way normally the stress or strain, whether extension, okay, or shear strain, the shape change we define. But what is essentially going to happen with this process of definition, in this way of definition, is that we do not know whether the deformation is essentially only just a shear or it has some rotation associated with it. It's possible that, anyway, before we go further, there are two types of strains which we consider. One, these strains, when we look at it, these are all maybe strains may be very large. Okay. Generally, we can consider the strain as an infinitesimal one. When we call a strain as an infinitesimal strain, what we mean is that the value is so small that product of these strains, either longitudinal strain or the shear strain, either product among themselves, okay, we assume that they are negligible and can be neglected. Okay, that is the assumption. Okay, and this is mostly valid, or you can consider it operates in most of the cases where the sample is elastically strained. Okay, then another part of the strain, which we call it as a homogeneous strain. Okay, the homogeneous strain is one in which we look at the strain which is homogeneously applied throughout the crystal. This strain has a lot to do with transformation of the material. Okay, like many types of phase transformations, we have to consider this, like morphostatic transformation or twinning are examples where this homogeneous shear concept is being employed. That I will come to later when I talk about them. For the present, let us look at only this infinitesimal strain. Okay.
Infinitesimal strain.
Yeah.
So in that you have mentioned that this is valid for elastic strains except at points which are only a few atomic distance from a defect. So
yeah,
if there is a lattice point which is a few atomic distance from a defect, then this kind of strain will not.
For example, when we think of dislocation, at the core of the dislocation, the displacements which are taking place, maybe the strain may be of the order of 50%. Okay. Generally, when we use generalized Hooke's law, the assumption essentially is that the linear elasticity can be applied and the stresses and strains are extremely small. That is why we make the assumption that this is valid normally throughout the crystal, but around defects there can be strains which can be very large. Okay, how do we define an infinitesimal strain? Okay. So with respect to coordinate system, okay, if we have a point, the line, that is we take on the object a small vector PQ, okay, by applying some stress, okay, there is a deformation, the point P under the action of a force, it moves to P dash and this moves to a point Q dash, okay. Suppose x and y are the coordinates of the point P. The coordinates of P dash will be, this is actually an exaggerated diagram, it could be very small, it could be x plus u and y plus v will be the coordinate, and where u and v are the displacements. The u is very close to P, so that we can write it as dx, x plus dx y plus dy. Okay. Then what is going to happen is that this point now it will be x plus dx plus u plus du plus y plus dy plus v plus dv. This is how it happens. Okay. Essentially, from this what we can make out is that the displacement which is taking place to any of the coordinate, you take it to be u, okay, in that direction has a component from, okay, forces which are acting on the other directions as well. This is essentially like if you have function u, okay, is a function of x, y and z, we can write that du will be equal to, okay, dou u by dx into dx dou u by dy into dy we can write it in this form, correct? In this fashion we can write it for v also. dv will be equal to dv by dx into dx dv by dy into similarly dw in all these terms are nothing but the rate of change of u as a function of x. That means that is nothing but an extension, that is nothing but a strain which is taking place in the x direction, okay. The component, what is the displacement which is taking place. Similarly, this one du by dy is, what does it define? It defines in the direction of u, but from a component corresponding to whatever is taking place in the direction of y, correct? So this can be represented as nothing but components of a strain, okay. This will be a component of a strain which is in the x direction. What is the displacement in the x direction, okay. The another is displacement in the x direction, contribution from the y direction, displacement to the x direction, that is in the displacement to the contribution to u, okay, from some deformation which is taking place in the z direction component.
So, for example, EXY,
yeah,
which is du by del u by del y.
Yeah.
So, in that the force will be perfect. The force, but the force has to be.
No, now we are not talking about the force at all. Any component of a strain, if you see it, the strain essentially is that Exx is essentially an extension which is taking place in the x direction, okay, the x.
Of the length scale that is in.
Length scale, that is displacement which is taking place in the x direction. Now another is contribution to displacement in the x direction could have come from something which is happening by a shear strain, okay. You can have a contribution to displacement in the x, contribution to u, the displacement in the x direction we can give it, correct?
Yes, sir, but u still, the length scale is still along x. Del u by del y.
Yeah, du when you consider is essentially a displacement of x in the x direction, okay. V is the displacement which is there in the y direction. W is the displacement in the Z direction. But that will have a contribution from strain which is taking place in that direction, plus some part of a strain which is also contributing, that could be a shear strain, that direction. Okay. So that is what we essentially write it as. I am just writing only these components. This is Y, Z, okay. These are all these terms. Exs will be du by dx, Exy equals, that is essentially with respect to some change in the x position, what is the displacement to u, some as a function of position in y, what is its contribution to u, that is the strain in that direction, that is Exy. We can define it this way. And in fact, you will find that there are many representations are being used. One has to be very careful about the type of representation xy and z which is being used. There are a lot of confusions are there in the literature, okay, especially with respect to stress. Okay. So essentially what we have, we can have 9 components of strain are possible, correct. Each of these component need not be equal also. They can have all different values, it is possible. But to understand it a little bit better, let us just consider a two-dimensional case. In the two-dimensional case, what happens is that then du will be depending upon du by dx, only this part of the equation, essentially only these two have to be considered, correct? Suppose we assume that the sample itself is just a vector pq, okay. And this vector pq deforms to pq dash it becomes, okay. Then what are the contributions which it can have? Because since we are considering it as a vector which is going to be in this direction, y direction is dy is going to be 0, correct? So then this equation turns out to be du will be dx dv equals dv by, correct? In this, if you look at it, okay, this represents only just u, what is the elongation. Okay. Now it has reached this point, right? P remains the same, q has reached this point. That means that some component of extension is there along the x direction. That component is being given by Exs into dx. What is the component which is going to be there from here to here? Okay. That is being given by Eyx. That component itself, we can consider it as, if there is, it's only a line, it could be considered as a rotation. I can just consider this line as taking it from here to here, okay, extend it this much and give a rotation to it, then also this can be reached.
So,
yeah.
P is transforming to Q and then Q.
No, here it is essentially what we are taking it is that the PQ is becoming PQ dash. P is fixed.
So then there is no displacement along x.
Which one?
So then there is no displacement along x.
No, PQ. see it is like this. You take PQ, okay, it reaches a point PQ dash. If it extends to Q dash, you will have some displacement which will be there in this direction, right?
If it is goes beyond Q.
Yeah.
Okay.
That is what we are considering. It is a vector PQ, okay. The position of the vector after some elongation is in this direction, okay. Then the question which comes is that we can find out what is the component of extension in the x direction, okay. That is essentially nothing but a longitudinal strain, correct? And what is going to be the component in the y direction, okay. But that component could be as well as just a simple rotation, it could be. So that means that this strain what we try to represent it, yx, it could be a shear strain or it could be a rotation also. It's something that it need not completely represent, whereas Ex's definition is very clear. Whereas all the other terms, when x is not equal to y, yeah, then there is a problem. It could represent anything. What is the way in which we can separate between rotation and shear, pure shear? How it can be done? Okay. That is, if we take any component Eij, okay, I not equal to, this can be written as half Eij plus Eji, because this sum total essentially is becoming a Eij only. Essentially is actually a shear, okay, Eij, and this part of it nothing but only a rotational component, which is essentially the body rotation. So that means that whenever we look at a whenever we see a displacement from one position to another, okay, and the displacement is changing as a function of position, then only we can see that there is a strain, correct? If the displacement is uniform throughout the sample, irrespective of the position, that means that there is no strain, only the sample has moved from one position to another position. If the sample has, with respect to sample has moved from here, there is a displacement, you assume it to be something like delta. Any point if you consider, from this point it has displaced by delta, and from this point also it has displaced by delta, right? So that means that the displacement is uniform throughout the sample and it is independent of the position. Then there is no strain. So strain comes only then the displacement is a function of position. Okay. So now we can consider it in, we can understand looking at a geometrical construction. Okay. And another important fact also is that when we take terms like this Eij and Dji, we had initially, now we had 9 components are there in this case, okay. Now if we take each of these terms to be equal to half of Eij plus Eji, then this part becomes a symmetric tensor, correct? Off diagonal values will have some other value, but these terms are all going to be, that is diagonal terms can have different values, but off diagonal terms will all have the same value, correct? Each one of them. Is it clear? So this we can look at it with a geometrical construction. So the geometrical construction what we have taken is, here if you see that dashed lines represent the, now I can draw it also. you assume that these are all the coordinate system which we have chosen. Okay. I apply a strain which is going to be take 1, 2. Okay. These are all the two components of the strain which is being applied with respect to. Then one which has a shape which is maybe whatever be that you take, assume it to be a square. Now it has changed the shape to a different shape, the sides of it, correct? This, if we take the product of this, not product, if we take the half of the sum of these two strains, okay, and then try to do it, essentially what will happen is that it is equivalent to as if changing it symmetrically by a strain half into E12 plus E21. This is equal to epsilon ij, the same way we have deformed it, correct? This is different components of the strains are there, all the 9 components are different. So E12 is this component, E21 is this component. So this coordinate has moved to this position, this coordinate has moved. The same operation we perform by taking the strain to be the symmetric part of it. Then it is essentially by the same half into E12 plus E21, we have moved this, okay. This has shifted to this position, okay, maybe by a shear vector. Now to this, now if we give a rotation, okay, what is the rotation which we give it? E of Eij plus Eji, okay. This rotation, what it will do it is that which was initially in this position, now it will rotate it to this position, okay. This will be rotating. So essentially similar to what has happened here, okay, the same shape change has been achieved in that. That in fact with respect to a figure which is being shown on the slide, you can understand it much better, okay. Here you can make out from the shape that obviously that Eij what is being taken, okay, is larger than Eji. Okay. Now the symmetric part, essentially half into Eij plus take it. So this vector has been essentially sheared, that is from which is parallel to it is sheared and brought it to this position, the same position it has been brought, and that is what is shown by the black line. What does the red line show is what is the rotation which is being given. Now if you look at it, both of them is similar to the original position. So essentially quite often when we look at the general 9 component of the strain which we consider, actual shear which is required with respect to a symmetric case, if we consider it, is only a shear part of it, or the strain which, not shear, the strain which it undergoes is being given by the symmetric component, and the other anti-symmetric component is part of it is just a rotation, okay. This actually happens in the case of a normal simple shear which we do it, okay. What do we do, like this case which we have considered here is that this is a square, okay. We have applied a shear stress and it has sheared, and this is the strain which we call it. This strain we generally call it as an engineering shear strain. This engineering shear strain is nothing but equal to, with respect to a tensorial strain if we consider it, it is corresponding to some pure shear plus some part of it is actually a rotation. This clarity should be there in this concept. Quite often when an engineering strain we apply, okay, actually part of it may be the pure shear which is occurring, other part may be just a rotation, or the physical significance of it is that if you try to deform a material, up to a certain extent it can accept the strain by compression, expansion, shear, pure shear and all. When that cannot be done, it will try to twist or rotate. Okay, this happens in most of the bodies. That is, when we look at a deformation of a polycrystalline material. Okay, at the middle of it, mostly strains will be there. Closer to the grain boundary when we come, when the matching between the boundaries have to be maintained, and suppose the boundaries on the other side is very hard, the only way it can accommodate is by just a rotation, rigid body rotation. But rigid body rotation is also equivalent to a strain. But with respect to whether the material has really undergone a strain, no, correct? So if we write it in this particular format, if we try to change it, then what we are able to see now is that actual strain which is taking place, the material which is being strained, that is the either it's a shear strain or whether it is a pure strain, okay. That plus a rigid body rotation is the, see, when we look at the displacement of a position, the displacement could take place due to a straining of the sample, due to shear of the sample, plus by a rotation, okay. Finally, what we measure is only this displacement. We do not know what the components are. So what we are trying to do it is that here in this expression, if you try to see it, this is what we are looking at it is with respect to some position change, what is going to be the displacement which is taking place in that. That's all which we are looking at it. Yeah, that displacement could have the components which are corresponding to it. From this expression, it's not becoming very clear what it is going to be. Okay, but each has got different values. So what is the jugglery, mathematical jugglery which we can do it? Is by taking it as a symmetric and an anti-symmetric part of it. We are able to separate this into rigid body rotation plus pure strain part of it. Okay.
So the symmetric part, is it like pulling equally along a diagonal? Let's say we have a square.
Okay. See, the symmetry part of it, pulling equally along a diagonal, there are many ways in which it can, I will just come to that. Okay. If I take a square, okay, apply a pure strain, okay, an extension. That's why the pure strain you find that there is no rotation part comes. The rotation part is coming for all the off-diagonal elements only. Off-diagonal elements we can't say whether it's a shear or a rotation or it is a combination of both. That is what we are trying to do by this mathematical operation. This we can give some elongation in this direction, some elongation in this direction. Okay. It becomes a rectangle, correct? Now what we are trying to do it is that apply a stress in this direction, okay, that is shear stress in this phase and shear stress in this phase, okay. Then what it will happen? The shear stress in this is essentially going to deform this to a parallelogram will come. The same parallelogram, but now the components, if you look at it, what are the components which you have? Pure elongation plus some shear is also there, okay. Both have been combined together to get a parallelogram. By along, that is, this is the axis which you have chosen to represent, or the coordinates which you have chosen to represent the sample. Okay, with respect to this, we can choose another coordinate, okay, inclined with respect to it, but perpendicular to each other, to which we can apply some strain, okay, elongation in one direction and perpendicular direction. If we give compression, the same shape change could be achieved. This shape change is essentially equivalent to giving just only pure strain but no shear strain. correct?
Sir, but like if the original square, right?
Yeah.
If you pull it along the diagonal and then rotate it,
Yeah.
so this is what we will get.
That will be a parallelogram with sides equal.
So here the sides are not equal.
Sides will not be equal, correct? So some angle difference will come. For an infinitesimal, the type of strain which we consider, it will be almost the same, close to it. So essentially what we are trying to do now is that a deformation which this square has undergone involves pure elongation or pure strain plus a shear strain, okay? And that same shape change can be introduced into the sample by applying a pure strain along some other axis, correct? So that those axes we call it as principal axis, okay? This is just a schematic diagram just to tell that how this can be achieved. Okay. The lower half, if you look at it, here what we have taken is that essentially a pure shear has been applied. By this pure shear, what we have done is that is whenever we apply a shear, what happens? There is going to be a change in shape of the sample, no change in volume. Whenever we apply pure strain, there is going to be a change in volume will be there, if it is going to be different in all the directions. If we apply a compression in one direction and a tension in another direction and adjust it in such a way that there is no volume change, then the same shear strain, whatever is the shape change which has been brought about here, has been achieved by tension along tensile tension in this direction and compression in this direction. It could be achieved, right? But the axis now, if we look at it, with respect to here, the shear stresses are acting along these axes. Now in this particular case, the axes are perpendicular at 45 degrees with respect to it, correct? So what I wanted to indicate from this is that even though we will have a, in a general case, we will have a shear strain as well as tensile or compressive strain, okay? Choosing an appropriate coordinate system, okay, which we call it as the principal axis, along which if we apply just dilatation, okay, we can bring about the same shape change.
Sir, but how is it maintained? Like in the example that we saw in the parallelogram,
Yeah.
the sides are not equal,
Yeah,
for example. But
yeah.
this one by definition will make the sides equal, right? These two operations.
These two operations will make it. There the axis may be some other axis you have to do it.
To get the same parallelogram, that parallelogram.
Yeah.
Okay, we have to just, instead of this one, we can just change.
The axis may not be exactly, now here the axes are 45 degrees with respect to it. There may be some other rotation which may have to be given. Essentially, at some angle with respect to a coordinate system which we have chosen, we can apply just dilatation,
Simple dilation and we
get the same. That dilation has to be, will be one tension in one direction, and compression in the other direction, okay. So that's what, in the case of a square here, what is going to happen is that it will be exactly 45 degree, okay. So that is what, in this particular slide, what I had just taken is only the symmetric part which I have taken. Because the symmetric part shows what is the strain which the sample is undergoing, okay. And the diagonal elements represent, okay, nothing but the dilatation, and the off diagonal elements represent just the pure shear component, or this is called as the dilatation is called as the pure strain component, okay. So when a pure dilatation takes place, there is going to be a volume change, okay. When pure shear components are going to be there, okay, then no volume change but only a shape change. And in this case, when both all the components are going to be present, we will have a volume change and a shape change, right. So essentially, from this what one can understand is that any symmetric strain matrix could be written in terms of just pure strain. Okay. This is also called as a diagonalization in matrix. Okay. Symmetric matrix can be to diagonal elements. Okay. Then when we do that, roots of that matrix are going to be the solution to this equation, correct? So here now epsilon 1, epsilon 2 to epsilon 3, 3 are going to be values which are going to be different. So if we choose a cube with such a shape, okay, and apply these principal strains in those directions, what will happen to the cube? The cube will become rectangular parallelepiped, right? That's what the shape which it's going to take. What is the volume change? It is nothing but if its dimensions are of unit dimensions for the cube initially, then the volume change delta will be okay. So what I was trying to tell is that when we have a symmetric second rank strain tensor matrix is there, okay, with 6 components which are present, okay, choosing an appropriate axis, okay, we can convert this into just pure strain along 3 axes, okay, with which the same shape and volume change could be achieved. Okay. In such a case, then the matrix becomes these diagonal elements are represent only just pure strain along these principal axes. Okay. If we choose a sample, okay, with the coordinate system corresponding to these principal axes, okay, and if we take a cube and allow them to undergo these strains along this direction, okay, then what is essentially is going to happen is that the cube will try to become nothing but a rectangular parallelepiped. Okay. The volume change which is going to take place is essentially nothing but the sum of epsilon 1 plus epsilon 2 plus epsilon 3, since the other cross product terms are going to be negligibly small. Okay. Generally, whenever we consider this a strain in any direction, any coordinate system, if we choose it, okay, suppose I choose an arbitrary coordinate system, okay, and take a cube of a material, okay, and try to deform them. What is the shape this will take? Because it can have both, on each of the faces it can have shear as well as a strain. All the faces there will be going to be a change which is going to take place from here to here. Okay. This face will undergo a change from here to here. Okay. Then this face will undergo a change, this face will undergo a change. I have not drawn it correctly, but all of them will undergo a change. It will become something like a parallelepiped. That is what I had shown, a two-dimensional case which is a parallelogram which it comes, correct, earlier. But when we take it along a principal axis, then these shear strains are not going to be there. Okay. But generally, if you look at the strain matrix which is represented, in many textbooks which you can see it, that gamma, the engineering strain which is being measured, will be shown as a matrix which will be shown consisting of, this is the form in which it will be shown. here these terms are all engineering terms, shear stress. Okay. But quite often, technically if you look at it, these stresses, if it's a symmetric matrix, this is going to be, each of the term will be nothing but half of this epsilon ij plus this one, that will be written. Okay. But strictly speaking, if you look at it, that's not correct, because it can have some rotational components also. So that doesn't represent the pure strain tensor. Okay. The strain tensor has to be written in this form only, the strain tensor is being written. Okay.
This is what they are terming as engineering.
This is what here that because when you write as technically it looks like that same, but there is a problem which is going to be there, is that engineering stress and strain, okay, and the actual shear stress, there is a slight difference is there. The difference which it comes is because of this. If I take a sample, deform it, this is the angle theta, okay. So this tan theta is nothing but the engineering strain, correct? Suppose we assume that this is a square, okay. This square itself can be applying a strain which is equal to half this value in this direction and half this value in this direction. I can bring about a this is just a pure strain, shear strain only. Okay. That is, if this is gamma, this will be gamma by 2, this is gamma by 2. Okay. Both these directions, this shape has been, both of them together simultaneously in this. So this is the component of the strain in this direction, shear strain, this is the component of the strain in this direction, correct?
So in this case, inherently we are assuming that gamma xy and gamma yx are same.
Irrespective of whatever be the value, if you take half, they will be symmetrical. Now what we have done essentially is that only one strain, this is only the strain which we have applied it. That is, we have taken a sample and given a deformation in this direction. Okay. We are trying to find out what is the strain which is going to be there in that direction. Okay. This strain, okay, this engineering strain, what I am trying to tell you is how it is related to pure strain. Okay, how this shape change can be achieved, let us look at it. This shape change can be achieved by giving a half by 2 shear strain in this direction. In this direction, a shear strain of gamma by 2 in that. So it has achieved this shape. Okay. Now, if I give this shape a rotation of gamma by 2 in this direction, what it will happen? Okay. It will now come back to this shape, it will reach, correct? Similar to the what it has happened here.
But I am not sure if it will come back to the same position.
It will come back.
It has to.
It has to. Absolutely, there is no problem about it. This, if you see, this is by theta, it has been rotated, this is by theta, correct? By some angle phi we have done this, okay? And now, if I give another rotation of phi after this shape has been reached, if I give a rotation of phi, this part of it come down to this position, original position, now it reaches, okay? Now what is the difference? This is just a shear strain, okay? This plus this, if you take it, is equivalent to the same, but both are applied in two different directions. So they are not the same tensor really. You understand that. Magnitude looks like the same. Takes out to be magnitude, turns out to be gamma by 2 plus gamma by 2. But the directions in which each of the gamma is being applied, gamma by 2 is being applied, are in two different directions. So that is what the actual pure strain is, the shear strain is. But engineering strain is only in one direction we are doing the measurement. So we cannot replace with engineering strain writing it to draw matrix like this. It's not the correct way to do it. Mathematically it has to be written as.
So then why don't we just use the original strain? Why aren't
No. What I am telling that the original strain only should be used. The reason essentially is that many books they give that matrix in this form. One should not be confused with that, that's all.
I am confused.
Eh?
I am confused with this actually. Even from long time I am confused.
With what?
With this notation I just simply don't understand which one is which. So now in this case all I am clear is that the definition that we give in those set of equations, that is what we should rely on.
We should not depend on the pure strain in the sample when you go. You rely upon what is being defined with respect to the axis. Okay, what we are defining it, go with respect to that only. The reason essentially is that here if you take this gamma engineering strain is nothing but equivalent to giving in any particular direction gamma by 2 shear, gamma by 2 a shear in another direction, plus a rotation of gamma by 2. You understand that? So both doesn't become equal. So use only the pure. If you wanted to find out just the strain part of it, use the strain. What is the definition which is given by the strain tensor only has to be used.
So can we use the symmetric part of it? Just to, no sir, I am getting confused. The symmetric part is the two strain. Two strain meaning it is just the pure strain part.
No, that is these diagonal elements give just the pure strain. There are two strains.
When I mean pure strain, I am separating between shear also. I am considering shear also as pure strain. No, I mean
It's a pure shear strain.
pure shear strain.
Pure shear strain.
And it is coupled with rotation. Right?
When we do an engineering strain measurement, pure that shear, simple shear when we do it normally, this I will come back to it. The simple shear is what we do in an engineering application. Just take a sample, that is if it's a two-dimensional object, apply a homogeneous shear, then this gets deformed to this shape, okay, and this is what we define, this angle theta equals tan theta. This is how we define an engineering strain. This engineering strain is a combination of pure shear plus a rotation. That's what it is. That is why whenever we wanted to talk with respect to the strain which the sample is undergoing, the rotation part has to be removed. Rotation part is, the sample is undergoing only a rotation. It is being sheared and rotated. So what we do measure in these ones is only the displacement. Na? From that we are calculating it. So the displacement always inherently has got, from displacement if you try to look at the strain, shear strain, that has got a rotation part plus an actual shear part is going to be there. That is the one which one has to be always careful about it. Whereas if we see with respect to any extension in these directions, this has no rotation. So whatever you do it, the engineering tensile strain and compressive strain becomes equal to just the tensorial strain, you can use that, but not the shear. That's what essentially wanted to tell them. Okay. So what have we looked at it in this whole lecture of about an hour? That is, what we measure is simple engineering strains which we measure, either elongation, okay, from that we can get the tensile or compressive strain, and shear strain which we can measure. Okay. Then those values, okay, now what we look at it, from that we can get the strain matrix, we can find out the components of it. That is because the shear strain part of it always has got both a rotation as well as pure shear which is going to be there. See, if you look at the matrix which we have written here, only the off diagonal elements we are taking this sumna, whereas the diagonal elements remain that same. There is no problem with that. So that is because the shear is the part where we have this rotation part also comes. So a pure, a simple shear need not mean that an atom has undergone some deformation. It might have undergone some displacement, and the total displacement which it has undergone could be some due to pure shear plus some due to rotation. Okay. So considering it as a pure strain which the sample is undergoing, then it is going to be only what the pure shear as well as the pure strain which the material undergoes. That is given by only this symmetric strain tensor. The other part of it essentially the rotation part of it. Yeah.
So the rotation matrix also, the rotation
Yeah.
component that we see,
Yeah.
even that is dependent on the amount of shear that we are applying, the amount of engineering shear we are applying.
Yeah.
Right. So if in the sample at different points you have different amount of engineering shear applied. Let's say in some deformation process. So the rotation will, the local, see this is not.
Yes, that is what it happens when you deform a polycrystalline material. When you take a polycrystalline material and deform, the interior of the grain undergoes just pure strain, whereas the close to a grain boundary, it undergoes rotation. The rotation in the interior, the center of the grain will be almost zero, but the maximum rotation will be there. So that's going to vary.
So it's a varying unit.
It's a varying unit.
It's not like a complete rigid body rotation.
No, but what has to happen is that this has to adjust itself in such a way that the total deformation remains that same for the sample. That is, if I have a sample which contains different types of grains, okay, if I try to give some extension, elongate it, at some strain rate I am loading it, okay, then all the grains have to undergo equal deformation, then only it will be uniformly, the length will be increasing. If some grain is so hard that doesn't happen, what will happen? The sample will fail. That's what can happen. Ultimately, that's what it can. If that should not happen, what it should do is that the one which is not able to undergo the elongation, they may try to rotate and adjust it. So every grain will have a component of epsilon ij and mega ij. These together will define the total strain, which you can call it as Eij, I will write it, the total corresponding to the externally applied. This has to change. So this strain to be generated in each one of them, some systems will be activated depending upon whatever is the direction which is favorable for slip to occur in that sample. You understand that? So that is how the deformation in a polycrystalline material will take place. Is it clear? So essentially the whole exercise of or the whole aim of this lecture itself is to find out or to have a clear understanding of actual strain and the engineering strain which contains rotation, and how these things can be separated into, and we can get that information. And essentially we have 9 components, independent components will be there, okay, and that itself can be divided when we take the rotation part out, okay, then separate the rotation and the pure shear, then we can write it in terms of a symmetric tensor, then we will have 6 components of strain are going to be there. Okay. Out of the 6 components of strain, if we find out one of them we can fix it, others will all be dependent on them. Okay. So that is why that 5 independent slip systems which we talk about will come because of that. Okay. We will stop here now.